Hey YouTube, welcome back to my LeetCode series. In this video we're going to solve question number 253, meeting rooms number 2. And these questions where we're at right now is we're at the merge intervals category of my LeetCode prep. I have already finished these categories and I've solved these problems without recording them, so I won't be recording them because the point of this series is for you to see my thought process and what kind of questions I ask and how I get myself from the brute force solution to the optimal solution. So the point of this series is really to teach you how to effectively problem solve and critically think through LeetCode, because memorizing solutions will only get you so far. Eventually you'll come across an interview where you will see a problem that you've never seen before and you'll need to be able to solve it. So yeah, if these videos help you, please make sure to like and subscribe for more content like this. So let's hop into the question. So I have a screenshot from Grokking. This is the same question from LeetCode, it's just a different resource. And the question says, given a list of intervals representing the start and end time of n meetings, find the minimum number of rooms required to hold all the meetings. So for the first example, we have 3 meetings, 1 to 4, 2 to 5, and 7 to 9, and we output 2 because all the meetings can be held with 2 rooms. So since 1 and 4 and 2 and 5 overlap, we need 2 rooms to hold the meetings. And 7 and 9 can occur in any of the 2 rooms later. So let's just draw this out so we understand the question. We have a meeting from 1 to 4. We have a meeting from 2 to 5. And we have a meeting from 7 to 9. So we see that we need 2 rooms because these are overlapping. And that means we need 2 rooms, maybe room A, room B, and then room A or B can be held for the third interval. Let's go to the second example. So we have 6, 7, 2, 4, and 8, 12. So my first question I'm asking right now, and I'm thinking, is this test case any different than the first one, 10, 11, 12? And the answer is yes. This test case, example 2, is different than the first one because there's no overlapping in the second example. So we can have 1 room. So this tells me if there's 0 overlaps, we can do 1 room. If there's 1 overlap, we can do 2 rooms. And I'm assuming the number of rooms is identical to the number of overlaps. Let's check the third example. Third example is 1, 4, 2, 3, and 3, 6. So here we are going to need two, since 1, 4 overlaps with the other 2 meetings, 2, 3, and 3, 6, we need 2 rooms. I see. So in this case, how do I select this? 2 and 3 would be something like this. Sorry, 2 and 3, and then 3 to 6. So technically, we can hold A here. We can hold B in that room, and we can hold this meeting in A or B as well. So in here, we have 1 overlap, which means 1 room. So in this example, these 2 rooms do not overlap because they start and end at the same time. And then let's draw the last. That was example 3. The last test case. Let's draw it down here. we have 4 to 5, 2 to 3, 2 to 4, and 3 to 5. And we return 2 because we can do A, B, and then A, B. So technically the number of overlaps we have are 1, 2, 3 overlaps, but we only need 2 rooms. And the reason why is because, sorry, this can't be held in room A, B has to be held in room A, and this can be held in room, we'll need 1 room for 2, 3, and 3, 5, right, and then 1 room for 2, 4, and 4, 5. Right, these diagrams are a bit skewed. It should be something like that. So then the number of overlaps is still here 2. 2 overlaps means 2 rooms. So I'm wondering if this heuristic fails in any example, that the number of overlaps is the number of rooms we're going to need. If we have here, we're going to need 4 rooms to hold these meetings. And then we'll need a 5th room right here. To be honest, I think this is going to work. Just counting the number of overlaps. The thing is, though, is we can't just count the raw number of overlaps, because what happens if we need 2 rooms to hold this, right? There's 2 overlaps here. There's another 2 overlaps here, so that means we have 4 overlaps in total, but we still only need 2 rooms because the overlaps only happen at different times. So this can be room A, B, A, B. So really what we have to do is we have to count the max number of overlaps at one time. This is what we need. This is equal to the number of rooms which we want to return. And actually another test case that I just thought up of is, what if you have something like this, where there's 3 overlaps in succession, but the first meeting ends before the 3rd meeting starts, so we can do ABA. So really what we need is the max intersection between a specific max intersection. I think this question is basically max intersection, where the intersection is the intersection of any 2 meetings. But the thing is, we don't have inputs like A and B, so we can't use a 2-pointer approach with A and B, but maybe we can use a 2-pointer approach within the array. But my new idea is the max intersection of rooms. So if we had something like this, no, not the max intersection, it's just the maximum number of rooms that overlap at once. So you see here, this window, all 3 are occurring. So then we're going to need 3 rooms to host all meetings. So the brute force way, I don't know why it took so long of just stating this out, is to loop I from 0 to n and check how many, and then we have a count equals 0, and we loop j from I plus 1 to n, and if intervals I and j overlap, do count plus plus. And then what we do is we have a max count up here. We can set this to negative infinity. And what happens is max count equals the max of max count and count. And then we return the max count. So this is the brute force naive solution because we are iterating through all possible combinations and counting the max. We are counting the max number of overlaps at one specific time. So in this case, this is 3. In this example, it is 2. And yeah, this is just 1. This is 0. And this is 1. And then the max number of overlaps plus 1 is the number of rooms, plus 1. So this is going to work, but the time is going to be n squared, and the space is going to be constant. So now the question becomes, can we do better than the brute force solution? Optimal solution. Possible times are maybe n log n, O of n, O of log n. And space could be constant. I don't think, it'd probably be O of n or something. So looking at the n log n solution, would it help if we sorted the intervals first? So we don't have to brute force all possible pairs. If we knew something was sorted, let's see, what am I trying to draw? There's a few test cases. But I guess the main idea first is let's just isolate the case where we want to count the number of max intersections for some specific interval I. So if we're at I equals 0 right here, we want to count how many intervals I intersects with, even if there's a bunch of other stuff right here. And the way we do that is simply just so we can set something like I equals 0, and while I is less than intervals dot length. What we can do is, so we would actually need a for loop to loop through all of the intervals. And what happens is candidate interval is equal to intervals at I, right? And we want to check how many intervals overlap with specifically I. We don't want, if we have something like this, we want the count for I equals 0. So we want the count for I equals 0 to return 1, not 3, because even though these are mergeable and they all overlap, we don't want that information. What we want is just the number of intervals that overlap just with I. So here in our code, what we would probably want to do is have a while loop and maybe like a while true, or just an inner loop. Let j equal I plus 1, j is less than intervals dot length, j plus plus. And we say if the current interval equals something like intervals at j, we say if the current interval starting time occurs before, not equal to, but just strictly less than, because meetings can start when other ones end. If the current interval starts before the candidate interval's ending time, then what we do is we do count plus plus. So we have a count equals 0 here for the number of intersections. And then, otherwise, we want to break out of this loop. Then we want to have a max. So we'll just name this max intersections. And what we'll want to do is check max intersections. We want to update it if necessary. So max of intersections and max intersections. So then I believe this solution is O of n log n with constant amount of space. And usually with these interval questions, it seems to be the best solution seems to be n log n with constant amount of space. I don't think we can get a linear runtime without, we can't get a linear runtime with some extra space, because in order for us to check the number of intervals that intersect with one given interval, we're going to have to search through all of them. So the only way to cut off that search time is by sorting it first. Because once we know, if we're looking at some interval, let's say right here, once we know the next interval in the sorted array does not overlap with the current interval, then we know how to skip on and we can cut that search time. So yeah, I think this is the solution. I'm going to code this up and we'll see if it works and then check the optimized solution. So let me zoom in here for you guys. We first want to sort and then find max intersection count. So we'll sort it first, 2 intervals, and then we'll loop. Do we need access to I? No, we don't. We do, for the inner loop. Okay, and then we have max intersection count equals negative infinity. Actually, no, we'll start at 0, and then we'll turn the max intersection count plus 1. We'll then have a temporary variable here, and we'll have a loop from j to 1. So also, let's see, this is technically 2 for loops, but what we can do here is, if we have rectangles that are like this, then we want, if we start the search at I equals 0 here, and then I is equal to 3 here, we don't want to increment I just by 1 to 1, because we've already searched this entire, we've already done all the work. So we would probably want to skip to I equals 4. So what we want to do here is we would probably want to set I is equal to, here we'll let j equals I plus 1. And then what we would want to do is, so do we want a for loop here? It's kind of getting messy at this point. Something like that. So while j is less than intervals dot length, and current interval and intervals at j dot start is less than intervals j minus 1, or not j minus 1, just I dot end, then we would do simply just j plus plus, j plus plus, and intersections plus plus. And then at the end, we would, j is now pointing to 4. Let's say 4 is like this rectangle that doesn't intersect with any of these. We want to set I equal to j minus 1, so back to 3, and then it'll get incremented to 4. So if we do that, then the runtime of this would be O of n. So this would be O of n. And sort would be n log n. So that's what we'll do. We'll let j equals I plus 1. And while j is less than meetings dot length, and the meetings at I, or meetings at j dot start occurs before the ending of the current meeting, we'll do intersection count plus plus, and we'll do j plus plus, and then at the end we'll set I equal to j minus 1. And then while we're done calculating the intersections for the ith meeting, what we'll do is we'll update the max intersection count with max intersection count and intersection count. So I believe that is the solution. Let's run it. Two, 1, 2, 2. I don't even know what the expected answers are supposed to be. Okay, so the first answer is right, that's 2. 1, 4 is supposed to be 2, that's right. 6, 7 should be 1, that's right. 1, 4, 2, 3, 3, 6 should be 2. I outputted 3. And then 4, 5, 2, 3, 2, 4, 3, 5 should be 2, that's right. Okay, so the answer I got wrong was the third test case. So why did I get that wrong? Let's just draw this out. So we have 1, 4, 2, 3, and 3, 6. I think I know if the meeting start is less than meetings end. This should be returning 2, because the max intersection count should be 1, and then we return that plus 1. But for some reason the max intersection count, I think this, in the third test case, the algorithm thinks that all of these 3 intersect. 1, 4, 2, 3, 3, 6. So the intersection count, yeah, for 1, 4 is 2 when it shouldn't be 2. Let's just make sure the meetings are fine. Okay, so that's fine. 1, 4, and 3, 6 intersect. Oh, I see. So the thing is that we have 3 intersections for interval, for this interval right here. But we can, even though there's 3 intersections, we can get away with 2 rooms because the first meeting ends before the second meeting ends. So then I wonder if it's the minimum number of intersections. For this test case, the minimum number of intersections is 1, but we would still need to have 4 meeting rooms for this case right here. So we need the max number of intersections that overlap at once. So I wonder, once we know that the 0 and first intersection overlap, we have some sort of end, and we have some sort of candidate interval. So we have some sort of candidate interval, which equals candidate meeting is equal to meetings at I. And we set the candidate meeting. We use the candidate meetings n right here, and we'll set the candidate meetings n to equal the minimum of the candidate meetings end and the current meetings end. And then this way we make sure that the count that we are counting includes intervals or meetings that happen all at once. Because if we have something like this, where we have this test case right here, right, where we have some sort of enclosing meeting, and technically there's 3 intersections happening at once, but the thing is these 2 can occur in different rooms. They can occur concurrently, or they can occur concurrently. So once we find that these 2 intersect, we set the max end to be right here. So anything that needs to be counted for this intersection needs to be with that space. So let's try running that and see if it works. Candidate meeting, not I, just candidate meeting. And then meeting at J, meetings. So we get 2, and let's uncomment these test cases to make sure these work as well. Cool, I think that's the right answer, 2, 2, 1, 2. 4, 5, 2, 3. 4, 5, 2, 3, 2, 4. 3, 5 should be 2. 1, 4, 2, 5. 7, 9 should be 2. Oh, this is the same test case right here. Yeah. So, yeah, this works. Let's look at the solution. So that's n log n and constant space, I believe. So we sort the intervals, and then we merge. Oh, and they merge overlapping meetings. Whoa, they're using heaps? Wait a second. Does my solution not work for multiple test cases? Let's search up the solution. So what happens here is they sort the array and then they create a priority queue of numbers, which I believe the priority queue is the rooms. So they loop through the intervals, and if the heap is empty, then they increase the count by 1, and then they offer the current interval. So the heap is not a heap is the heap of intervals. If it's not empty, then we check if the current interval happens after the smallest interval in the min heap. If it does, we pull that interval off, and then after we push, we offer our current interval. Otherwise, it doesn't, so they overlap, so we just increment the count and still offer that to the interval. I see. So it's a very simple heap question. So what the heap does here is the heap gives access to the smallest interval, and we need a priority queue and not a simple queue, because it seems to be here the problem is here when 16 to 23 is put into the queue, it wastes the time here because 9 to 29 can start earlier. So this green space is wasted. If we inserted 4 to the queue, no, we inserted 2, 15 to the queue first, and then we're at 4 and 9. 4 is not 4 is greater than or equal to 2. The heap is not empty. So if 4 is greater than or equal to heap.peak, which the comparator is comparing just the start time, then technically 4 is greater than or equal to 2. So then they pull 2 out. That doesn't make sense. Oh, they offer the ending time. So yeah, if 4 is greater than the ending time 15, it's not. So we're going to increment the count by 1, which is 2 rooms. And then the heap is going to be 4, 9. So then if we were dealing with a heap, we would come across 9, 29 first and check to see if 9 is after oh, I see. So we check to see if the red start is later than the black end, because the min heap uses the min heap uses the ending interval, and 9 actually goes and swims up to the top of the heap because 9 is less than 15, because we're dealing with the min heap. So we want to compare the start time of any interval with the end time, the smallest end time. If we didn't and we had a regular queue, then 9 would technically we would be comparing with 15, because 15 was the first thing inserted with the first in, first out. And then we would be returning 3, which is wrong, because we can actually return 2 here. The solution that I had was that I just don't know if my solution is right. Let's see with this test case right here. Okay, I can't really find the answer if this solution works or not. Anyways, it's definitely n log n. I just don't know if this solution with constant amount of space works for everything, or if we actually have to use the min heap to keep track of the smallest ending time so far. But regardless, I'll look into that. But I hope this video has been helpful nonetheless. And if this has helped you in any way, please make sure to drop a like and subscribe for more content like this. So yeah, I'll see you guys next video. Peace.